Hey guys, welcome. Yeah, so this is a pretty cool video because we're gonna learn how to derive the equation of a plane in this video. I'll make at least a couple of additional videos showing you real examples, but in this video, since it's example 0, we're talking like the concept. We're gonna use visuals and ensure that you really understand what the equation of a plane is all about, that you really understand what you're doing. Yeah? Okay, cool. Let's start with this visual. So what you need is two vectors in your plane. And of course, if you have 3 points in the plane, then it's easy to get two vectors in the plane, right? You just subtract the coordinates of A from B to get the vector AB. And then you subtract the coordinates of A from the coordinates of C to get the vector AC here. And using these two vectors, we can find their cross product. So we take the cross product between these two vectors, and then we get this vector n, which is not only perpendicular to these two original vectors in the plane, but also perpendicular to the plane itself. So this vector n is perpendicular to our plane. And so then we call n the direction vector. Yes, it seems odd that we're calling something perpendicular to our plane the direction vector, but in a way it is a direction vector because it uniquely identifies a plane, right? Like if you have a vector n that is perpendicular to a plane, then that vector n is not perpendicular to any other plane. It's only perpendicular to one plane. And so that's a good way to pin down our plane. Yeah? Okay, cool. Now, very important is that you get to this vector n, and again, you get to n by taking two vectors in your plane and doing the cross product between them. But then once you find n, what you want to do is find another vector, which we're going to call p, by taking any point on your plane whose coordinates you know, and then a random point on your plane whose coordinates will be x, y, z. Okay, so maybe that didn't make sense, but here's what I'm saying. So let P be a point x1, x2, x3, where you know the actual numbers x1, x2, and x3. That could be point A here. So P can be point A, P can be point B, P can be point C. Any point on your plane whose coordinates you actually know can be the point P here. And then x, y, z is a random point on your plane, right? And so then if you do the difference between the coordinates of x, y, z, the random point on your plane, and then this point P, whose coordinates you actually know, then you make this vector P. Yeah? Okay, because remember, the goal is to describe any point x, y, z in our plane, right? To describe it in an equation. And so to describe any random point, we need to work with a random point whose coordinates are x, y, z. And then we like put the arrow on that point x, y, z, and then put the initial end at any other point whose coordinates we know, and then we make this vector P. Okay, what can we say about this vector P? Well, what we can say about any vector in our plane, which is that it must be perpendicular to this n vector, right? Any vector in our plane must be perpendicular to this vector n, and therefore this vector P must be perpendicular to this vector n. And we know that two vectors are perpendicular means that their dot product is 0. And therefore we see that our vector P and our vector n, when dotted, have to equal 0. And this is how we're going to get to the equation of a plane. Because from n dot P equals 0, we have first this visual. Let me help you with this visual, right? Like, well, we're going to get to the equation of a plane from n dot P equals 0, but I'll do that like in a second after we talk about this visual. This is what I was just saying in a vacuum, which is that like the random point on your plane, let's say it's right here, and its coordinates are x, y, z. Then by taking the point B as being this point P with x1, x2, and x3, so B can be this point P, right? And so taking B and then this random point xyz, we form this vector here whose arrow is at xyz. But then there was nothing special about B playing the role of this point P here. we could have used C or A, as I said. And so we could have used this other purple vector pointing from C to the random point x comma y comma z, or from A. And if we dot any of these purple vectors with n, then we should find that the dot product is 0 between any of these three purple vectors, and n, the dot product is 0. And that's what we're doing basically here. We're saying that x1, x2, and x3 are actual numbers we know. And so like this represents a random like similar a vector to one of these purple vectors, right? Okay, so any of these three purple vectors is the vector p, is what I'm saying. Yeah, okay, cool. Okay. I think you get it. And so let's move on. And so, having this vector p and dotting it with n, we know it has to equal 0. And so going on to the next slides, we can pick up where we just left off, which is here. And we know that n will have, if we're in 3D, n will have 3 components. And let's say that the components of n are called A, B, and C. Then, as we just said, n dot p has to be 0. So that's that. And of course, performing the dot product, that is multiplying A with x minus x1, and then B with y minus x2, and C with z minus x3. We know that the product of those things added will have to equal 0. Sorry guys, I'm stuttering, I'm a little tired. And so that means we have to have this. Basically, this dot product right here set to equal 0 will give us this here. And this is what we call the Cartesian equation of a plane. As you can see, if we distribute A, B, and C, and then collect all the constants on the right side, we'd have this version of the Cartesian equation of a plane. And of course, letting D equal the sum of all the constants, we can have this equation or this equation as the equation of a plane. Yeah? Okay, cool. All right, this is it for derivation of the equation of a plane. Next will be a few examples of how to actually do this with actual numbers, right? Okay, cool. All right, I hope you enjoyed this, and yeah, keep watching. Take care.